Welcome to the last video for IB Physics about thermodynamics, which is about entropy and the second law of thermodynamics. Now, a quick definition of entropy is the amount of disorder in a system. There's a more complicated version, but that's what you need to know for this class. The more disordered a system is, the higher its entropy is. Some ways you can tell if entropy is increasing in a system is generally, if the temperature is increasing, the entropy is probably increasing. Because as you increase the temperature, you increase the amount of energy in the system, which means that you're increasing the number of ways that the energy can be distributed among all the molecules of the system, which is to say, you're increasing the disorder. Also, if the volume of a gas is increasing, that normally means entropy is increasing, because if there's more space, there's more places you can put all the different molecules, more different ways to arrange them, therefore more disorder. If something is either melting or boiling, entropy is increasing, because in a solid has very low entropy, because every molecule is in its particular spot, they never go very far, it's a very, very ordered system. Liquid is more ordered, or is less ordered than a solid, but it still has relatively low entropy because every single molecule is going to stay in the beaker. Whereas with a gas, very low, very high entropy, large volume, the molecules are not guaranteed to be anywhere near where they started out if you look at them, say, a minute later. So the gas has very high entropy. Anytime you have mixing of two substances, the entropy will increase as well. So if you've got a bunch of nitrogen gas in one half of the room and a bunch of oxygen gas in the other half of the room, and you let them mix together, there's more ways to arrange it where the nitrogen and oxygen are mixed together than there are when all the oxygen's in this half and all the nitrogen's in the other half. That means when they're mixed, it's higher entropy. So you need to know that definition. Now, the second law of thermodynamics says the entropy of the universe must increase for any process. So any process that happens must increase the entropy of the universe. Or another way of saying it, the entropy of a closed system must be increased by any process in the system. Now, what we mean by a closed system is that no heat is transferred in or out. And this idea of a closed system is very, very important, because if the system is not closed, a local decrease in entropy is allowed, provided the entropy increases somewhere else in the universe. And the way that you make entropy increase somewhere else is if heat is transferred out of the system. And that's an idea you need to know, is that when you take heat out of a system, you can decrease the entropy of the system. But if there's no way to take heat out of the system, then the entropy of that system has to increase. It's very, very important. It will be on the test. An example of this is water freezing. Now, we know that when water freezes, it goes from a liquid to a solid, and anytime you have liquid to a solid means that you have a decrease in entropy. Now, the question is, why does the second law of thermodynamics allow that? And in what cases does it allow? Well, if you've got your ice tray here, and it's in your freezer. Then in the process of it freezing, what happens is that heat is being transferred into the freezer. And that means the ice is not a closed system. As heat is transferred into the air around it, what happens is that the entropy of the air increases more than the entropy of the ice decreases. And the result of this is that the second law is not violated, even though the entropy of the ice does in fact decrease. The entropy of the air around it increases more. Now notice here that if the temperature of the air is greater than the freezing point of the ice, that heat transfer isn't going to happen, and therefore the second law of thermodynamics does not allow ice to freeze if the air around it is greater than 0 degrees Celsius. And a last thing that sometimes comes up is the question of whether or not the appearance of life on Earth violates the second law of thermodynamics. And it turns out it does not. And here's why. So here's the Earth. There's Florida, there's Greenland, there's Europe, Great Britain, Africa. Okay, it looks sort of like that. Anyway, we are going to take it as axiomatic that the development of life is very low entropy. A living human being has much less entropy than the equivalent mass of, say, dirt. The entropy of a cow is much lower than the entropy of a large number of steaks, or is much smaller than the entropy of a large number of steaks. However, the fact that entropy decreases on Earth is a consequence of radiation from the sun. So the sun heats the Earth. The Earth then radiates all of that heat, which is an enormous amount of energy, out into space. Into space, which means that the entropy of space increases a whole lot, and that allows the entropy of the Earth to decrease. And specifically to decrease without violating the second law. If the sun wasn't there, then life could not have arisen on Earth, because the Earth would not have been heated, and therefore would not be able to radiate energy and entropy into space. So what you need to know after this is a definition of entropy, the amount of disorder in a system. You need to be able to state the second law of thermodynamics, and you need to be able to explain why local decreases in entropy are allowed, and the heat transfer is very, very important to that. You need to mention heat transfer anytime you're asked about this on an exam. That's the last one. Next videos will be about nuclear physics, which is awesome.